the right answers, Mingchao.
Okay.
So we just have a few more
Hey,
panelists join.
Lucy,
Thanks.
Michael. Hey, Matteo.
Lucy, Michael, and Matteo have just joined.
Hello, everyone.
So
Thank you very
Matteo's
much for
also
coming.
in Edinburgh with Marcelo, and Michael's in London, and Lucy, well, should be in Marseille, but she may not be.
Yeah.
So
Can't you
thank
tell
you
from
very
the
much.
sun that's coming in?
It is. Okay. Thanks very much for joining, everyone. Yeah, so as Jimmy just said, we normally start by having a little bit of conversation with the speakers. So Mingchao, I think everyone knows Mingchao, but I thought it would be interesting to sort of get a sense from Mingchao because he has a lot of experience in lots of different systems and has done some research in different places and done some teaching in different places. So maybe Mingchao, I don't know. I wondered if you had any interesting and crucially maybe cheap lessons that we can learn in the UK from all the other places you've been. So you've studied and worked in Singapore and Australia, in China, and in the UK. Hi, Darren. Thanks very
Hi,
much.
Darren.
Hi, everyone.
Okay, so
sorry,
is
yeah,
this a question?
This is a question, yeah. So you've tried lots of different systems and you know what the good things and what the bad things are. And I guess the question, hey Doug, a question that I think would be interesting to hear a little bit about is what are the sort of the best bits about research environments in different places you've been?
Oh, actually, it's a hard question, I think. It's a hard start. So indeed, I have been experienced in 4 different countries, 4 or 5 different universities. It's there are quite a lot difference in different countries, different systems, and I guess one particular thing for all those guys in UK, we will know that we have quite limited resource. So especially compared to China, compared to Singapore. So it's quite challenging for, I guess, Michael has a very strong feeling. I guess somehow it's similar like myself. So it's very hard to get started smoothly. This is something I feel challenged, but on the other hand, I think UK also provides us a little bit more freedom since we don't get too much research support at the beginning, so they also leave us a bit freedom. For example, myself, our school reduced my teaching load from in the first year I have low teaching. In the second year, I have a few teachings. It's gradually increasing until this third year. I will get the full teaching load. So I guess it's somehow to be balanced the low support to reduce the pressure, I think. Regarding to the research environment, I think it's hard to say which place is better. It totally depends. In different university you'll find someone is doing good, someone is maybe it's not so good. But it's hard to say which place is best. I'm not sure if you guys have any opinion, but from my point of view,
It's okay. I know it's difficult to say which places. I didn't want to ask which place is best. I was trying to ask it in terms of what's good to learn, what are good lessons to learn. So it was very interesting to hear that that this kind of lighter teaching load is a good way to help people get set up at the beginning. So thank you. That's great. Yeah, I mean, maybe another difficult question then. I don't know if I'm being a bit unfair, but it's interesting. I mean, we'll talk about that a little bit later when I introduce you. But your PhD was in solid mechanics, but really in thinking about porous media and how flow in porous media kind of gives deformation and things. And then you sort of changed a little bit for your postdoc, and I guess thinking about sort of early career people who may be on watching the webinar or watching it later. I wondered if you had any advice for people making a change a little bit like that. You know, what's a good way to do that, and what do you wish you'd sort of known 5 years ago, maybe that you know now?
Okay, yeah, indeed, this is another challenge question. So actually, Changqing know much more about my my story. So I even during my PhD, I changed not too much, but I changed my topics slightly. Initially, we want to study the fracture properties of porous media, but finally I moved from that topic a little bit away from fracture to also include some fluid flow or something like that. So I guess one thing is important for the big shift since my PhD since my postdoc start to work with you. I think I made, as you mentioned, I changed it from porous media to basically to the cylinder structure system. I think this is not a yo-yo case because I can make this change. I think from my point of view, one big support is from the fellowship. So as you know, I get the Newton International Fellowship, so which gave me much more freedom to do what I would like to do. And also, I don't need to worry about too much. The topic is I know you know you are not so restricted supervisor, but I can from my point of view, if I'm working with you under your funding, I may not I mean I can, but I will have some pressure to try to force myself to more focus on what topic your funding is applied to. But since I hold in the fellowship, so I can more easily to make the decision what's the most interesting I would like to do. So I was lucky to hold those two fellowships. One is from the Royal Society, other one is from the NTU. So those two fellowships support my 5 years independent research. I think this helped me a lot to shift my research direction change a lot.
Okay, that's great. Thank you very much. Sorry, I should have said that we've had a few more panelists join us in the last few minutes. So thanks very much.
Yep.
Doug, Wei Cheng, Teng, Wei, and Jingda. It's good to see you. So I guess maybe sort of following on from that, Mingchao, I guess if the one question that sort of early career people listening might be interested in is what are the areas that might be interesting to move into in the next 5 years or something like that? Do you have any advice about that?
Okay. So I think this question is even more challenging compared to the last two questions. I do thought about these questions for a long time. I have a lot of conversation with Jimmy when I was in Singapore, and also I asked many people, for example, Hua Jian, and also the John Wennis from Cambridge. So asking those more senior people for their advice, what's the somehow the promising direction in solid mechanics for the maybe next 5 years. But to be honest, I didn't get any direct answer. For myself, I also I cannot easy to answer this question. But from my point of view, I also have some conversation with you before. I think you still remember. So I think as we know, for the instability of cylinder structure is an old topic, to be honest. But within this old topic, so there are still some emerging things are interesting. For example, what's the dynamics of those kind of instabilities? So we're also trying to push forward in this particular direction. But it's to be honest, it's not easy question. So I think it worth to explore further in the future. And another thing I get from not only my opinion by myself, I hear some seminars and also have some conversation with the senior people. They all told me maybe the living system, either the biomechanics or the active living system, should be or promising area in the next maybe 5 to 10 years. But again, this is I don't have concrete idea for what particular questions to do for this particular area. So this is my general thoughts I have before. Yeah.
But so if it's not about particular areas, are there particular tools that are kind of useful? And I mean, I guess.
Okay, so for tools,
that might be good. Yeah.
Yeah, so actually, I think what I learned from you is that the most powerful tool is your pen. Is that right? You can derive all the equations by your hand. But I think this is not easy for everyone. So for some people, they may be able to derive equations by hand for different problems, but for some other people, they may prefer to using some numeric tools to. For example, Wei Chen is a very good person to run simulation to solve different types of problems. So I think it's a good way to combine. It's a good way to combine the numeric tools and some simple theoretical analysis. In the future, I think, especially since last 2 years, I think the generative AI looks quite powerful. But how to integrate it into our research pathway, I think it worth to explore further.
Okay, so you're saying sort of using AI in mechanics sounds like a good idea, but the sort of practicalities of doing it or the kinds of questions that
I think
it can be used for is not so clear.
Yeah, personally, I think it should be a good idea to combine AI and some simple search model and some numeric tools like what Wei Chen is working on, the differential geometry or something like that. But how to combine them in a good way, I think, is still a challenge problem. There are some attempts in the last 3 years or 5 years, but it's so far I haven't seen some very concrete solution to combine them perfectly.
Okay, thanks very much. So moving towards a little bit the time when I might introduce you. So you've been physically in Birmingham for a year now, nearly a year.
Yeah,
is that right?
10 months.
10 months. Okay, so how's your group? And I guess you have some students at the moment.
Yes, so I physically start at Birmingham since last September. So I was lucky to get my first student before I joined in. So the student almost start at the same time as myself. So now I have one PhD student and one visiting PhD student. So it's not bad. So it's I think it's a good start. But still challenge, as you know, in the UK, hiring PhD students is even more challenge than hiring postdocs because our funding cannot support PhD. So it's I don't know when I will have funding to support the second PhD, but I will try myself. I will try my best.
Yeah, I think it's not easy at the moment, and the EU is one good way of doing that through the ERC and things like that. It's not an easy situation. So again, I'm sorry, I'm asking many difficult questions today. But I was sort of interested as well. I was interested as well if you'd say a few words about, I don't know if it's one of the things you might talk about later, but just interested to know what you're sort of proudest of research-wise. Is there something that you kind of get some satisfaction from, either as an application or kind of just technical achievement or something like that?
Okay, so I think it's not a simple question. I'm still struggling for the research direction, especially in the future. But at the moment, I'm still mainly focused on the cylinder structure mechanics, but focus more on the application side because when I was working with you in Oxford, but we are in the mathematics institute. So it seems that application it's also important, but it's not the priority. But when I moved to Birmingham, I'm based in the engineering department. So the application is the key, especially for founding application or something. So I'm trying to not shift, but trying to apply some of our knowledge about the central structure mechanics to design some functional structures, such as the soft robotics or something like that. I hope to achieve more in the application side in the next few years to make a stronger profile to fit the engineering department requirements.
Yeah, maybe that was another question I should have asked earlier about different departments and again in terms of research environments. There's a few people joined as panelists that again I should well first thank for joining. So Xiaohe and Bo, thank you very much for joining us, and apologies if anyone else has joined recently and I've not introduced you, but thanks very much for coming. Yeah, so I guess sorry, did someone say something? No, okay. So you also have kind of a bit of a broad range of teaching experience as well in different places. Is that mostly in Tsinghua?
Yes, this is not exactly true, because I do have some tutorial experience in Tsinghua and also now in Birmingham. But for teaching, I don't have too much teaching experience, especially for lecturing. So I do have the experience for giving lecture at Birmingham. And also I do some. I helped Jimmy on some. It's still tutorial, but looks like a lecture at NTU. So it's not too much. But if you want to ask my opinion of the feedback, I think I'm not. It's hard to say, but one thing I think it worth to share that recently in the last semester I gave some kind of guest lecture about the soft robotics at Birmingham. So it's surprisingly, I got very good feedback from the students. Finally, I go back to think about what's the reason the students get so positive feedback. I think recently for the students, it's easier to get information from, for example, from the multimedia information. So if you write down too much equations or descriptions on your slides, it's not so attractive for students, because it's not only for students, also for myself. It's if I'm listening a lecture or seminar, if I say too much equations on the screen, it's easy to get tired. So I think I got this impression from the students that for my lecture I put a lot of videos and pictures to demonstrate what the soft robotics can be applied to and what types of design has been proposed. So the students looks quite interesting about that kind of way. So I think this also to push, at least for myself, to think even if I in the future, if I give a lecture to do a lecture about even for a more fundamental course, not like soft robotics stuff. For example, I'm doing some solid mechanics or mechanics and materials course. I guess it's also better to include more interactive stuff into your materials, is rather than just put a lot of equations or descriptions something. It's much easier to get the attention from the students.
And it can be, I think it's maybe also worth saying that it can be useful for your own research to do that as well, sort of in terms of thinking about how to explain things and why and what's a good or what's a demonstration of things that there is.
That's true.
I know that I've seen or in my own work where I tried to think of a demonstration of something and then actually been able to use that as either as an experiment or as motivation for something in my research.
Yeah,
A couple
exactly.
more people have joined. So Yiwei Zhang, thanks very much for coming. And Wei Tan, I think you did come earlier, but you're back. So thank you as well. I don't know whether we're nearing 3 o'clock now, so I guess maybe it's time to think about Mingchao, whether you want to have practice sharing your slides, whether you want to try
I
that
can
now.
try to I can try to share my slide. Okay, so can you see my screen?
Yeah, it looks good to me.
Is that okay?
Yeah,
Yeah,
no
that's
problem.
perfect.
Yeah.
So you're sharing well.
Yeah.
I don't know what others plan to do, but I think I might turn my video off when Mingchao's actually talking, just to stop having too much distraction. So other panelists, please feel free to do that. I know you're also muted, but yeah, I plan to turn my video off once Mingchao starts talking. Sorry, that wasn't to say please do turn your videos off, but everyone has more or less done that now. Thank you. Yeah, so maybe I'll start and just introduce Mingchao a little bit. For those who've been on the call a little while, you might have heard some of this already, but I'll start off at the beginning of Mingchao's career, and then we can talk a little bit more about what he's done since then, and hopefully leading into what he's doing now at Birmingham. So Mingchao started with a Bachelor of Engineering from Shandong in 2013, and then he moved to Tsinghua, where he did a PhD with Chengqing Chen. And his thesis was titled Liquid Diffusion, Deformation and Fracture Properties in Porous Materials. But he also, during that period, spent some time in Sydney visiting Yishangang with an Endeavour Research Fellowship. And as we were talking earlier, that sort of involved a little bit of changing direction or thinking again about what the direction that Mingchao wanted to take for his PhD was. After he finished his PhD in 2018, he came to Oxford as a Newton International Fellow, where I was very lucky to be his mentor and to work with him and talk to him a lot about mechanics. That was interrupted by COVID, and so we didn't always meet as much as we might have liked. But then in 2021, he moved to Nanyang Technical University in Singapore with a presidential postdoc fellowship. Again, an independent fellowship, and Mingchao was talking earlier about how that's important for him to have been able to develop his research. But I know he benefited a lot from talking to Jimmy Xie and Hua Jingao and many other people at NTU, and really enjoyed that. And then since 2023, September last year, he's been an assistant professor at the University of Birmingham in the School of Engineering there, and that's where he is now, and that's where he's got his title slide showing us the sort of famous landmarks of Birmingham. So Mingchao, thanks very much for coming. I'm going to hand over to you and look forward to hearing about your work. Thank you very much.
Okay. So thank you, Dominic, for the kind introduction. So can you guys hear me clear?
Yes, Mingchao.
Yeah,
okay, great. Okay, so firstly, I would like to thank the editorial team of EML for making this journal outstanding. Also, I would like to thank Jen for organizing this wonderful EML webinar, the Young Research Forum. It is a great honor to be here today to give a seminar. To be honest, I'm a bit nervous, especially in front of my supervisors, mentors, and a lot of collaborators. So over the past 5 years, I have been attending many EML webinars, and I learned a lot from them. I hope I can also share some valuable insights with you in today's talk. Today, I will mainly introduce some recent works we have done, mainly focus on the bio-inspired design of morphing and moving matter. Yeah, so in this slide, I have summarized the research topics in my group is interested in. So we are mainly focused on 2 areas. The first one is about the mechanics of cylinder structures, including the beams, plates, shears, ribbons, and especially we are interested in the elastic instabilities of those kind of cylinder structures, particularly about the dynamic instabilities. So actually, this is a quite fundamental topic. And the second one is about applying our knowledge of the central structure mechanics to the design of some intelligent structures such as shape morphing structures, soft robotics, and mechanical materials. So we refer those kind of structures as the robotic matter. So in today's talk, we mainly focus on the design and modeling of morphing and moving matter. So first, let's look at the magic of the nature. So when we work outdoors, we can see many living things, such as various plants with diverse flowers and leaves, as well as different types of animals and insects. Through millions of years of evolution, they have developed rich morphology features and some efficient locomotion modes. So I borrowed this video from BBC Earth, showcasing the extraordinary animals and plants in nature. So watching this video, I was amazed by the greatest wonder of the natural world. Made me think about how can we learn from nature. It's really amazing. So actually, while saying we can make our life better, it might be too ambitious for a short period of time, but we can certainly explore how can we learn from nature to improve our engineering design. So this is a question we would like to answer in this talk, briefly. And in recent years, there have been many explorations in the bio-inspired design, such as bio-inspired medical devices, bio-inspired soft robotics, and also some bio-inspired materials. So one particular question we aim to answer is, how can mechanics help us to understand and also mimic biological systems? So, okay, so we will start our journey in this little garden. You can see that this is created by ChatGPT. So this is the generative AI help us to express our ideas. So by showcasing 4 examples, we will demonstrate the design and of morphing and moving matters by mimicking nature. So our first example is the design of a morphing structure with the foldable behavior, so which is inspired by the bamboo leaves. I will explain in details later. So when we talk about morphing structures, you may think about transformers. Indeed, transformer is a very typical example of morphing structures, but it is quite advanced. So in the real lab, research lab, you will say that what we are studying recently is much more simpler. For example, this is a lattice structure which can change the topology by responding to the external stimuli, or even simpler, a tubular structure that can be deformed by stretching. So we can refer to this as morphing structures. So the reason we are interested in morphing structure is because they have shown great potentials in research areas. For example, if we have an airplane with a morphing wing, it can be much more energy efficient, and also morphing structures can be applied to the soft robotics to make it more to perform more diverse functions. So as we mentioned before, plant leaves exhibit the rich morphologic features, providing the great inspiration for creating morphing structure. So for most of the leaves, the shape formation is based on the stream mismatch, similar like this to this bilayer system. So this stream mismatch is triggered by the differential growth of the cell. So a notable characteristics is for those leaves is that their shapes are normally smooth, as you say for those examples. So you cannot see any sharp change of the curvature. So one natural question arises for us is, how can we achieve the localized shape change? So the answer comes to me one day when I was working on the campus of NTU in Singapore. This story goes back to around 2 years ago. So I still remember after a group meeting with Jimmy, I was working from the office to my apartment. I noticed that a dry leaf of this kind of plant, it named as Rapis excessa, is very common in Singapore and also in some southern part of China and so in Taiwan. So it shows a significant folded shape. So compared to the fresh state, you will say the shape changed quite a lot. Initially, in the fresh state, it's almost flat, but in the dry state, it forms very significant zigzag shape. So this is a common folding behavior. So you may also observe this behavior somewhere else. So what we want to do is trying to understand what's the reason of this kind of folding and how we can learn from this kind of folding. So to quantify the folding dynamics, so we cut the leaf sample with different lengths. So we first measure the change of the folding angle. Here is the delta theta as a function plotted as a function of time. So as you see, the results here show that the sample with different lengths exhibit almost this similar trend. So the angle always increase with the time and eventually reaches a plateau. However, the folding, as you see from those curves, the folding happens faster for the shorter sample. The top one is a shorter sample. So this is intuitive because, as we know, for the cutted leaf, the water mainly evaporates from the exposed cut edges. So for longer samples, the liquid will need to transport from center to the edge. But for shorter samples, the liquid is easier to evaporate from the edge. So we also measure the water loss rate, water loss ratio as a function of time. So we observe the similar trend as the angle change. So interesting thing is that, as you see, they look quite similar. So we plot those two groups of data together. So interestingly, we get this kind of linear correlation. So this linear correlation is quite significant and also important because based on this correlation, so if we normally, if we want to predict the angle change, we need to know the microstructure information of the leaf. But from this correlation, we can, instead of predicting the angle change, we can just predict the water loss. When we get the prediction of the water loss, we can use this correlation to reflect the angle change dynamics. So here we propose a simple mathematical model to describe the water loss of the leaf during the drying process. And as we know that the water can evaporate from either from the edge or from the top and bottom surface. In the real case, actually, those two source of the two pathway of the evaporation are coupled with each other. Here to simplify the problem, we consider them separately. For the water loss from the edge, we can develop this kind of, we consider the water loss from the edge, and we can develop a very simple mathematical model. And we can show that from here, you see this is the water loss as a function of t. So from here, you will see that the time t is dependent to the length of the sample. So which means the kinetics of this kind of water loss is depending on the size, the length of the sample. So here you see the original data. We plot the water loss as a function of t. They are separate for different sample. But if we divided the time t by the length L, so we can collapse all the data onto our single mass curve. So which reflects this, our simple model can capture the main physics of this this water loss process. For the water loss from the surface, actually it's independent of the sample size, but it also follows the exponential trend. We get a similar equation to predict the water loss, but here the time is independent of the length L. So next, we want to understand the folding mechanism more clearly. So by taking the optical image, as you see here, so we can identify the most significant volume change happens in this area. So we refer this area as the hinge cell. So all other areas, such as those two parts, also involve the shrinking, but it's not as significant as the hinge cell. So for the this circular area is a vein. You may know from the in the leaf, the vein is rigid. It cannot shrink during the drying. It will keep the rigidity and also keep the volume. So that means the stream mismatch between the hinge cell and the vein will contribute to the folding of of the leaf structure. So to test the hypothesis, so here we develop two FEM models. In the first model, we only introduce, as you see here, we only introduce the vein structure, which is rigid and will not shrink during drying. So as you see, the other part will be shrink. Here we use the thermal strain to reflect the volume change. As you see here, when we increase the when we make those two parts shrink even up to 40%, we didn't see any significant folding. In the next model here, we introduce a hinge cell, which reflects this hinge cell region near the vein. So the hinge cell will shrink more significantly, significant than this all other cell region. As you see, with this hinge cell, by applying the hinge strain, so we can trigger very significant folding. So this is those simulations confirm that the folding is mainly induced by the shrinking of the hinge cell. So except for the folding, we also observe the bending of the leaf, such as this part. So by taking images of the deck cell and back cell of the leaf, which is the deck cell is the surface face to the sunlight, and back cell is the face is opposite to the sunlight. So by taking images of those two surfaces, we will find that they have quite different surface properties. As you see here, for those back cell surface, it has quite a lot stomata, which is some small holes will enhance the evaporation of the water. That means during the drying process, this surface may shrink more than the other side. So by accounting these features in our FEM model here, as you see, we introduce the biolayer model. The adapt cell side shrinks less than the back cell side. So we can achieve this kind of bending similar to what we observed from the experience. So since the back cell side shrinks always shrinks more than the adductor side, so those leaves always bend to the bottom side. So if we combine our understanding of the hinge folding and the bilateral bending into our FEM model, as you see here, we can fully reproduce the morphology evolution of the leaf during dehydration in our FEM simulation. It shows that our FEM simulation agree quite well with the experimental observation. So far we fully understand, from our point of view, we think we understand what's happening of the folding in this particular leaf. You may wondering what's the reason of this kind of folding? Why does this leaf want to fold? So to be honest, we cannot answer these questions properly, but here we propose two potential reasons for, we refer to it as the biologic function, the potential biologic functions to explain why does the leaf wants to fold. So as you see here, the first one is that the folding will increase the rigidity by the geometric constraint, which can be reflected by a simple piece of paper. If you introduce the hinges, it will the rigidity will increase a lot. So the second one is that the folding plus bending of the leaf will reduce the reduce the water loss. This also confirmed by our control experiments. So both two mechanisms help the plant to survive in extreme environment. So this is our hypothesis. So based on our previous understanding of the folding mechanism of leaf, we can create the biomimetic foldable device. So as you see here, so we combine the EcoFlex with hydrogel. The hydrogel initially is fully saturated with water. During drying, the water will evaporate and the volume will shrink. So here forms the stream mismatch. It will induce the bending. It will induce the folding. So by applying this kind of design, so we can create a device which can be used to detect, to measure the humidity in this environment, since the folding angle is depending on the humidity. So another example is that we can create this kind of responsive umbrella. So the working principle is that it will fold upon drying. For example, in a sunny day, your umbrella will fold by itself. When it is raining, so it will unfold spontaneously. So you don't need to worry. You will be you don't need to worry about the raining. So we hope that this kind of smart machines will be used in our daily life in the future. So actually, foldable structures exist widely at different scale, such as protein, DNA, and brain all involves quite a lot of foldings, quite a lot of folds. So instead of those kind of natural structure, in engineering, foldable structures also show great potential for applications such as those foldable wings and also foldable solar panel. So for those applications, normally we need to consider the dynamics. So here are two examples of the foldable structures. If you check those foldable structures in details, you will find that most of the foldable structures exhibit a single mode of folding. So they can do either continuous folding or snapping folding. For continuous folding, it is stable, but normally slow. It's not good. But for snapping folding, it's fast, but normally it will induce a strong vibration. So we are considering whether we can achieve a foldable structure with tenable folding, which means we can transition from one mode to the other or the other way around. So for this purpose, we proposed a concept called as the meta ribbon. So I will explain it in little details. As shown here, we found that if we introduce in-plane kinks, so here is the in-plane kinks. If we introduce these in-plane kinks into our annual ribbon, as you see here, we can trigger the continuous folding. It's quite smooth and stable. And we did some stability analysis and found that this kind of smooth continuous folding is covered by the supercritical pitchfork bifurcation. So on the other hand, if we introduce the auto-plane creases into your annual ribbon, so as you see here, we can trigger the snapping folding, which is quite fast, but here we don't consider dynamic effects, so you didn't see the vibration. I will show that later. So by doing the stability analysis, we found this is governed by the subcritical pitchfork bifurcation. So by integrating the in-plane kinks and auto-plane creases together into a single ribbon, we can create this kind of meta ribbon. So the foldable behavior of this meta ribbon is tenable, as we mentioned. Here is an energy map we generated by our numeric simulation for a particular meta ribbon. As you see here, we marked different paths. So that means you can choose different paths to achieve different types of folding. Here I put several examples. As you see here, if we fix the auto-plane angle as, for example, 60 degrees, and then change the in-plane angle, so we will follow this path. This is definitely all continuous folding, so it's quite smooth. But if we fix the auto-plane angle as 120 degrees, and still we change the in-plane angle, okay, so you see we achieve this kind of snap folding with a strong oscillation. In the other way, we can fix the in-plane angle at different values. We can also achieve either the snapping folding or the continuous folding. So this is a very typical example to design this kind of tenable foldable folding behavior in a ribbon structure. So in that section, we have demonstrated the design of morphing structure with foldable behavior. So now we would like to explore the design of more general morphing methods. We will show later where we get this kind of inspiration. So morphing structure has become an emerging topic in recent years. Here I include several examples which enabled by different types of extra stimuli, such as the numeric expansion, thermal expansion, and also the swirling of the hydrogel. So even just applying mechanic load combined with the Kurigami technology or Kurigami concept, a complex 3D structure can be achieved. This beautiful work has been done by Yi Hui and his collaborators around maybe 10 years ago. So to realize the inverse design, we also have done some simple theoretic model based on the Elastica theory. So those models works quite well. It's also powerful, but it can only apply to the axisymmetric condition and only apply to the simple curvature distribution. So we are wondering if we can achieve a morphing structure with general 3D shapes by using simple principle. Okay, to get the idea, so we go back to this garden. We found that this turtle shell looks quite interesting. It's composed by multiple blocks. So each block has particular shape. Putting those together, we can form this kind of shell. So this kind of principle has been adopted in old days. For example, this kind of arch bridge is made by stone bricks, stone blocks with particular shape. So as you see here, so this kind of arch shape can be formed by assembling those stone blocks together. Each block has particular geometry. So we can use this kind of principle to design morphing structure. You can see from here, this kind of principle only involves a geometric relation without any elastic information. So actually, this principle has been tested by Yifan's group. So they tried to translate those 2D and 3D structures into particles. And by controlling the geometry of each particle, the curvature can be matched. So in experience, so they printed all the particles and put them into a plastic bag. By vacuum the bag, all the particles will be squeezed to stay together, and then they can form the target shape. For 2D geometry, it works quite well, but for 3D, it's basically it's quite challenging to form a large curvature. The reason is quite simple. According to the Gaussian remark theorem, if you want to deform a flat, for example, here, if you want to deform a flat shape to a curved one, you need to space to store extra materials. So you can imagine that if you want to design a full spheric by using this kind of way, you will encounter some problems since no space to store the materials of the bag. So to overcome this problem, so we get inspiration from biological system. So we propose a new design principle named as the hierarchical tessellation. So what we are doing here is like we choose a sphere as our target. So we first cut it into multiple pieces at the global level. So each piece is in a curved state. So as you see here, so to match the curvature, we tessellate this curved piece into individual particles at the local level. And then, so if we assemble all those particles together, we can match this curvature of each piece. So this is similar as what we mentioned about the arch bridge. So as you see here, if we assemble all those particles together, so we can form the target shape. So actually, this kind of design is quite simple, and each particle can be fabricated by using 3D printing. So it's quite easy. So you can choose how many particles you use, and you will see more particles. How many pieces you cut, more pieces you will make the final structure more close to target. And also we can introduce the geometry interlocking, which will enhance the rigidity of the morphed structure. Here we show a simple example. So to make the sphere, we printed all the particles and placed them on a flat plate. As you see here, for each of the particle, we leave 2 holes at the 2 edges of each particle, and then we insert a tendon pass through those holes. So when you pull the tendon, all the particle will be pushed together through contact with the neighbors. So as you see here, here's a video. When you pull the tendon under this, so all the particles will be pushed to stay together with the neighbors. So here we can see the flat state and the morphed state of the 3D morphed 3D shape, and also this is from the top view. So translating into more pieces at the global level, you will get the final structure more close to our sphere. And we can also introduce a geometry interlocking. And here I would like to emphasize one point is that, as we mentioned before, this kind of method is purely geometric. It doesn't involve any deformation. So in principle, it is scale independent. So we can scale it up or down to any size, but in reality, it depends on your fabrication technology. So what we can do by using a normal 3D printer, we can achieve the sample size from maybe 2 to 3 centimeters to around 10 to 20 centimeters. So if you remember, the main purpose of this design proposing this design method is to achieve the general morphing shape. Here we show 3 examples. The first one is a groove shape. The first one is a groove shape, which is with complex curvature distribution. As you see, it changes from positive negative to positive again. So by using our design algorithm, we can test the target into individual particles and print them placed on flat state. When we assemble them together, so we can get this morphed structure looks very similar to the target. The second example is a vast structure, which is non-axisymmetric. So again, we can test it into particles and assemble together. So it's almost the same as target. The final one is a mushroom chair, which is much more complex since it is non-axisymmetric and also with complex curvature distribution. Again, we tested the particles and we assemble them together to form the 3D structure. So all those examples show that our design method based on the hierarchical isolation can achieve general morphing structures. So one more thing, one more advantage I would like to say about this kind of method is that the rigidity of the morphed structure can be adjusted. As we have mentioned before, we use tendon to actuate the morphing. So that means we can control how large the actuation force you apply to the tendon. As you see here, if you apply larger force on the tendon, so you will get the structure more, the morphed structure more stiff. So basically, we get this kind of linear relation of the stiffness of the morphed structure as a function of the actuation force. So which means we can shift the state of morphed structure from the stiff state to soft state, or the other way around. So we can also replace, if you remember, we use the tendon to apply the actuation. Here we replace the tendon by a shape memory alloy wire. So those wires are stretched initially, and then when we apply the voltage, it will be heated and get shorter to trigger the morphing. So we can also change the stiffness of the morphed structure by controlling the voltage state. The final thing I would like to highlight here for this kind of method, this kind of morphing structure, is that it can be applied to electric device. As we know, the fabrication of the curved electric device is a ground challenge. But here we fabricate all the particles on flat state. That means we can easily print electric circuit on the planar state like this, and then make it morph to the 3D shape. We can perform the function in the 3D state. Here we show one example. We printed the circuit and integrated LED light onto the morphing structure at flat state. Initially it's flat, so each particles are separated. So the circuit is not conducting. So once it morphed, you will see the particle will contact with the neighbors. So the circuit will be conducted. So the LED light will be turned on. So when you release the actuation, the particles will separate again. So the LED light will be turned on. Okay, so far we have shown 2 examples of the bio-inspired design of morphing structures assisted by the mechanics principle. Actually, there are also some other mechanics principle can be applied to design morphing methods, such as stream mismatch, elastic instabilities, origami or kerigami. So today, due to time limitation, I only include two of those mechanisms. We have done quite a few explanations in the past few years. If you are interested in, you are welcome to read those papers. We also wrote a review paper on this topic, published in Soft Science. So feel free to take a look. So now we shall move on to the design and modeling of moving matter. So in particular, we are considering the locomotion of robots. So the first example is a jumping robot with excellent performance. So as we know, robotics, or especially the soft robotics, is a promising topic and has been become an emerging area in recent years. So there are a lot of soft robotics has been developed in recent years. So the locomotion of soft robot is quite interesting. So there are 2 examples. So top one is a jumping robot triggered by light. and bottom one is a crawling robot triggered by magnetic field. So let's first look at the jumping robot. So we would like to design a jumping robot with high efficiency. As we know, for human, what we are doing, we use the squat jump. So this kind of mechanism mainly relies on the energy release of our muscle. To be honest, this is not so efficient. So when we go back to look at the garden, so we found one
But that's okay.
excellent
It doesn't
jumper.
have to. It's an insect that's famous for using its
This
body in a
video
spectacular way to
shows
get
that
off the
the
ground
click
and
beetle
back
can
on its
utilize
feet.
the snap-through ability to release the pre-stored energy. As you see, it can jump quite high. It's even more than 30 times of its body length. Compared to human, it's quite excellent. So we are wondering, can we design a jumping robot by mimicking this kind of mechanism? The answer is yes. So a group from UIUC led by Sam achieved this kind of design. So they drew the inspiration from the click beetle and then designed an insect scale jumping robot. The design is quite simple, as you see here. So this is an elastic beam. So in experience, it's made by steel. So initially this beam is flat, so we can compress it to make it buckle to a curved state. On the top is an artificial muscle. It will shrink when we heat it up. So it will, as you see, at the critical state, when you heat the muscle up, it will deform the two edges of the robot body. It will force the, it will push the beam jumps from the top to the bottom while snap through. And this process will release the elastic energy stored in the beam quite fast. Once the beam contact with the ground, there is a reaction node will generate and then push the robot to jump up. So here's a video to, as you see from here, this tiny robot can jump quite high compared to its body length. It's fascinating. So since we have done some more fundamental work about the dynamics snap-through of beams with Dominic and Michael, some contact us to say if we can work together to develop a search model to predict their tiny jumping robot. So for this, based on this kind of design, 4 types of robot can developed depending on the buckle shape of the beam and also with or without the pre-stored elastic energy. They all show good performance. So our goal is to develop a model to predict the jumping performance. So one option is to consider the full process of this kind of deformation from here to here. And also it involves the dynamic contact. So, but here we didn't adopt this option. What we did is trying to simplify the system, the robot system, into a mass spring model like this, which is quite simple. The key component are 2 mass corresponding to this central mass corresponding to beam and the edge mass corresponding to the body. So the energy stored in the beam is reflected by this deformation of this spring. So we can easily write down the Newton's second law to write down the kinetic equation for those 2 mass, and then by applying different boundary conditions, so we can solve this system easily. And here we show that by our model can predict the experiment data works quite well. So this data is for the displacement as function of time for different 4 types of robot. So one thing we need to notice that here is a free parameter K, which is the stiffness of the spring. It's a fating parameter. We need to fate it from the experiment data. What we did here is that we choose one experiment data point to do the fating and use that fated value to predict the whole group of data. It shows that the agreement looks quite well. So we can also predict the velocity as a function of time, also agrees quite well. So based on the results of velocity, we can also calculate the acceleration as you see here. So maximum value of the acceleration is quite high. It's even up to 250 G. It's a huge value. So one thing we need to, we can highlight here is that, for our, by using our model, we can do the optimal design of this kind of robot. So for this kind of robot, as you see here, one key parameter is this HR, which measures the distance between the bottom center point of the fully snapped beam and the edge of the body. So we refer this parameter as a restricting height. So from experience, we can measure the takeoff velocity as a function of restricting height, and our model can predict those trends quite well. So we also have two asymptotic solutions to consider the two extreme conditions, either for small restricting height or larger restricting height. By using this, actually, this graph shows that by applying our model, we can do the optimal design of the robot to achieve a good performance, even our model is simple. So the final example is a robot inspired by the millipede. So like this. So actually, this kind of multi-neck robot, as you see here, is multi-neck insect is quite interesting. So to mimic its locomotion, so a lot of design has been proposed. So one particular example is the magnetic Xenia robot. Here, those legs are made by the magnetic responsive materials. By applying the rotational, as you see here, by applying the rotational external magnetic field, those robots can move through either the rolling mode or the crawling mode. So these experiences are really beautiful, to be honest. But one challenge is that how to efficiently design a robot with good performance. So the traditional way is that by doing try and error in experience, we do 10, 20 rounds of experience to check which group of parameters are more efficient. So what we are thinking is to develop an efficient numerical framework to simulate the robot behavior. Here we adopt the framework based on the differential, the discrete differential geometry. This type of method is popular in computer graphics, for example, in making the movie special effects. Recently, it has been adopted in the solid mechanics community. Here we include the magnetic elastic coupling like this into the discrete elastic rod framework. And another thing is that since we need to consider the we also need to introduce elastic plate and also consider the interaction between the rod and the plate. So here we write down the coupling energy for the both stretching and bending, and then we can solve those system numerically. By applying those kind of numeric model, as you see here, so we can simulate the locomotion of this kind of magnetic Xenia robot. Here is the crowding mode. It shows that our simulation can successfully reproduce the robotic behavior. And since our model is very efficient, so we can run a lot of simulation in a short time to test the parameters. For example, we can test the effect of the frequency of the magnetic field and also the friction between the rod and the substrate to test those effects on the locomotion efficiency. So here we also proposed a strategy to achieve the non-straight pathway by controlling the actuation non-locally. So similarly, we can also simulate the rolling locomotion. We only need to change the, as you see here, we only need to change the distribution of the magnetization and also the stiffness of the plate. So then we can reproduce the rolling locomotion. So also we can test the different parameters, the effect of those parameters on the locomotion efficiency. So to be honest, this is just a very preliminary attempt on the simulation of soft robot. So we would like to push it forward in the future to, for example, to understand the evolution of the biological movement or to achieve the optimal design of those kind of robotic system. So here's a brief summary. Due to the time limitation, I will not read it all. So finally, I would like to thank all of my collaborators, especially the support from my PhD supervisor, Professor Chang Chen from Tsinghua University, and also my host supervisor, Professor Dominic Vella at Oxford, and also Professor Jimmy Xia from NTU. Okay, so thank you all for your attention. I would happy to answer any questions.
Thanks very much, Mingchao.
Yeah, thank you.
So, Yeah, okay, so there's a number of people with hands up. I think I'm going to go first of all to Changqing. If you want to ask Mingchao a question first, that'd be great. Thank you.
Thank you, Dominic. Thank you, Mingchao, for a very nice talk about morphing and moving mind. So I have two questions. So first one is actually on page 20, on page 10, you show a linear relation between the angle and the loss of mass.
Yeah.
On page 10. Yeah.
Yeah, here.
Yeah, sure. So does that mean there's only a geometrical effect? Because later on you show due to the mass loss, then you have some different strains. So is the ratio of the angle between the angle and the mass loss is a material parameter, or is it actually something else?
Okay, so first of all, thanks for your great question. So what I mean is the slope of this linear relation.
Yes.
Yeah, to be honest, we didn't consider the meaning of this slope before. But I think certainly you are right. It's somehow this is because, as you say, for different groups of data, they all sitting on this single curve. Probably this is some kind of materials property.
I mean, it might be that it's geometric as well, rather than sort of, because if you're, I think the idea is that you're losing material from the hinge cells,
Yeah.
or losing mass from particular cells.
Yeah.
So again, you're sorry.
No.
I think I'm just trying to point out that there are different ways of having material properties. It could be, it doesn't have to be sort of a mechanical.
Yeah, that's true. That's true.
It could just be a geometrical thing in the way that the cells.
Yeah, it's not like
as they lose mass.
Yeah, it's not like for example, the Young's modules or the intrinsic materials property, but indeed it's linked to those materials property and combined with the geometric effects to somehow come up with some sort of materials behavior. We cannot easily point it out as a materials property, but at least is a given materials behavior.
Okay. So I have a second question. So you mentioned on page 28 that your method actually can be used to design general morphing structure.
Yeah.
Basically, you show different types of morphing structures right here.
Yeah.
Yes. So my question is there any limitation of the method?
Okay, thank you very much. It's also
structure you cannot use this kind of design?
Yeah. I fully understand your question, and I do have a very detailed answer to this question because we have think about these questions for a long time. So as you see here, what I emphasize that we can make different types of geometry, but if you look at those three examples, they all don't have any very localized curvature change. So one typical example is that instead of this mushroom chair, initially we are planning to make a human face. So we want to reproduce a human face with the mouth, with the ears, a lot of localized geometric information. but it's quite challenging for us to achieve this point at the moment, at least. So we can do the tessellation, it's no problem. So we can tessellate any kind of 3D geometry into individual particles. But the challenge is about the actuation. For example, here we use the tendon-driven actuation, and for those kind of very localized geometric feature, it's really difficult to achieve the actuation smoothly. So we are still thinking, is there any alternative way, or is there any improvement to enhance this kind of method to make it more feasible for repeat those kind of local curvature? But we are still stuck there. We cannot achieve that point so far.
Okay, thank you.
Yeah, thank you very much.
Thanks very much, Mingchao, and thank you, Chengjin. Chengjin at NTU, do you want to ask a question?
Yes, Mingchao, excellent presentation. It's
Thank you.
very impressive to see how much work you have already done in this field. I do have a minor question regarding the first part of your talk on this dehydration-induced folding. We know if you have a structure made of conventional engineering materials, usually the folding behavior can undergo many cycles, right? Although it can fatigue over time. My question is for those biological systems, have you looked into this repeatability of the folding process? Is it really repeatable? How many times it can be how can undergo before it lose the folding capability?
Okay, thank you very much. It's another very good question. So indeed, we tried to test the repeatability of those kind of folding behavior, and it depends on if the leaf is still alive. So since, as you say, for our experience, so we need to, for example, here we need to cut it out from our complete leaf. So basically, we tried two types of experiments. One is that we keep this kind of whole petal of leaf, and then we do the drying, the folding experience by control the environment condition. Indeed, it's basically is repeatable, but I'm not so sure how many times it can be repeated, but at least more than 3 or 4 times is doable. But for those kind of cutted leaf, it's quite challenging, since once you've done one cycle of the folding experience, part of the cells are going to die. So it's not fully repeatable. So I think it's a good question for us to answer, is that if we can directly use this kind of biological system to behave like a machine, it's not to do some biomimetic design. So in that way, we definitely need to carefully consider the repeatability, or the how many cycles it can be reused. So we didn't. We consider that very preliminary. We didn't do too much concrete tests. So I think it's a good question for us to think in the future.
Yeah, thank you, Mingchao.
Yeah,
Can I jump in over here just to so I'm part of the team to work on this. In fact, when you cut the leaves, the fresh leaves, you can repeat this drying and rehydration process many times, as long as the leaves do not die, or the cells at the edge of the leaves. What happens is, after a few cycles of drying and rehydration, the edge of the leaves becomes black. Then the ability for the edge cells to absorb water would be compromised. Actually, Kexin Guo, the student who did the work, may answer the question better than I can.
Yeah. So all those experiments has been done by Kashin. It's Jimmy's PhD student.
Yeah, I think it would be interesting to look into what really happened at the cellular level, right?
Yeah, indeed.
Because when we set die for the cell, it's easy to understand from the organism level, a plant die, but what defines a die for a cell,
It's
especially
true.
the
It's
plant
true.
cell?
Yeah.
Sorry, we've got lots of hands up, so should maybe move on. Iwei, over to you, please.
Yes. Mingchao, congratulations on the wonderful work.
Thank you very much.
Very inspiring and informative. I have two questions, very small questions. And the first one is regarding the metal ribbon you have studied, which is very interesting to note that continuous folding show very different behavior from that of slap-through folding. So I was wondering how the loading rate or the release velocity affect the folding behavior.
Yeah, actually, it's a very good question. So, to be honest, here we didn't test the loading rate effect. We just, as you say, all those results are generated by numeric simulation. So we assume the actuation is almost very slow compared to the, as you see here, compared to the snap folding. I'm sorry, this one, compared to the short period of snapping folding speed. So the loading speed is much slower than this folding process. But it's a good question that we do have one figure in the supplementary of this paper. We test the different loading rate. Is that since as we know for the dynamic instability, we have some kind of delayed bifurcation. So you may observe, again here, you may observe the delay of this kind of snap-through instability. So, but go back to your question about how does the effect of loading rate on the folding dynamics. To be honest, we didn't explore that so far. So I think it's worth to have more concrete exploration in the future to combine the dynamic loading process into the dynamic folding process. Sorry, I didn't include the figure here, but we also observed some, for example, for those kind of foldable structures, they may involve the multiple stable states rather than two stable states. So we can expect that if you control the loading rate, you may jump pass through some of the stable states, and you may jump from the stable 1 to stable 3, and for those kind of things. I think there are still a lot of opportunities for further exploration in the future. Thank you very much.
Sure. A relevant question is for the vibration followed by the slap-through, how long does it take to stabilize typically?
Yeah, okay, so yeah, it's actually, as you see here, we generate this vibration by using dynamic simulation. So as you see here is a period of time of the vibration. This period of time is depending on the materials itself. Firstly, for example, the damping of the materials. If the damping is quite large, so you will not see any strong vibration. But when you decrease the damping, you will see stronger and stronger vibration. So firstly, it depends on the materials property itself. So the second is also depends on the geometric effect, as you see here. So for different autoplane angle fixed, as you see, 120 degree, you will get longer period of vibration. For some small angle, for example, 75 degree, you will get short period of vibration time. So in summary, it depends on both the materials parameters and the geometry itself. So we didn't quantify that in this work. I think, again, it's thank you very much for this kind of very good question to inspiring us to explore further in this system to quantify the vibration effect.
Sure, thanks.
Yeah,
The other
thanks very much.
question-
So
the
I
other-
just wanted to step in on there, if that's okay. Just to ask Mingchao. I mean, is it that that's the distance that it has to jump? So the 120 falling off a bigger cliff. So is that, if you like, it's
actually
a bigger cliff than the
here
blue.
I just exactly. It's not fully correct. Here you say the horizontal axis is angle. It's not the time, but we do have some plot to show the energy as a function of time. Basically, it's a similar trend.
Okay. Sorry, thank you. Yiwei, sorry, I wasn't sure if that was your second question or if you...
It's fine, it's fine. The second question is actually quite similar to Professor Changjin Chen's second question. So for the design principle you proposed to universally design curved surfaces. I noticed that most of your demonstration are closed form 3D surfaces. Because you want to introduce self-folding to create closed form surfaces. Is it possible to create some open 3D surfaces based on this design principle?
Open, you mean some, for example, the half spherical structure, something like that?
Yeah, like human face or seashells.
Okay. Yeah. Thank you very much. I'm sure that you know much more than me in this particular field. So my simple thought about this question is that indeed we can make the open spherical or open curved structure. It's indeed it's doable. As you see here, for example, this kind of west structures, the top and bottom surface are both with the open area. But again, go back to Changjin's question and also what you are interested in about making of face or something. I realize that in your work you have done quite a lot very wonderful surface and structures. So for most of the for some of those complex surface, this kind of method is still to be challenged because we cannot match the local, especially some localized curvature. For example, the air or for human face, you will see a lot of localized curvature. So to reproduce this kind of localized curvature is still a challenge. So we don't have a good way to solve this challenge so far. So hope we can find the answer in the future.
Okay, thanks. Again,
thank you very much.
On the wonderful talk.
Thank you.
Thanks very much, Yiwei. And thank you for the patience of the others who have their hands raised. Doug, do you want to ask your question?
Thanks for the excellent seminar, Mingchao. I was also really in your work on the kind of transition of the ribbons from a kind of continuous folding to that snapping. You know, ribbons are kind of in between plates and beams, and so I'm curious about how the role of the width affects things. What happens as it becomes more plate-like or more beam-like?
Okay. Thank you very much. It's a very wonderful question. Actually, as you see, we are considering ribbon. So at the moment, what we are considering, the width is around at least 10 times smaller than the length scale, but it's also 10 times larger than the synchrony scale. So your particular question about the effect of the weights on the folding behavior, as we didn't test that at the moment. We tried to. We are sure that for example, a certain range, for example, from 10% to maybe 1 or 2%, the weight compared to the length, our framework definitely works good. But for larger ribbon, or we refer this somehow it looks like a plate. We are not so sure if our principles still work. So we are after this paper published, our creators, we are talking about for the future work is to test the effect of the the relative weights on the folding behavior. Sorry, I cannot give you a very precise answer to this question. We hope we can answer this question in maybe in the next paper, next work.
Excellent. Thank you, Mingchao.
Yeah, thank you.
Thanks very much, Doug. Yifan, do you want to?
Yes. Hi, thanks, Mingchao. Thanks for the fascinating talk. So
Thank you.
my question is actually about the morphing structure. So you have mentioned a lot of interesting morphing structures, right? And we also published a paper together. So I remember that when we sent the paper to the editor or reviewer, they were asking us what practical things that you can make out of this that could be useful, right? And we were scratching our head and what can we make out of it? That's really useful. And when I actually think about it, so for these morphing structures, if we make it really small, like nano or micro scale, perhaps like what Yihui did with the microscale electronics, that's quite useful. Or if you make some like nano or microscale drug delivery devices, right? And if you look at the very large scale, huge scale, like aerospace structure, that's also useful, like satellites, deployable structure, things like that. But if we look at the scale in between, like the tabletop scale, and when we make something on this like centimeter or tens of centimeter scale like this, what can we really use it for? So at that time, we didn't have a very good answer. So I wonder whether you have now have a better thought about this.
Okay, yes, thank you very much. Yeah, it's also a very wonderful question. So I'm also always keep asking myself about this question. So I still remember last year when I visited Tsinghua, I also asked Yihui about this question. So I get quite a lot inspiring answers from him. So recently, I'm based in the school of engineering, so we have a department about the electric, and it's a double E. So so one professor in the electric department, they are working on the antenna. So it's some device to control the electric magnetic wave. So when I show some of our work to that professor, he's quite interested in our staff to use this kind of structure, for example, the morphing structure to be a reconfigurable antenna. So I think this is one particular thing, and we may be able to combine this design concept to the antenna design. This is one particular thing. Another thing I also get some inspiration from in your conference that some people working on the meta surface. This meta surface is used for control the reflection of also for magnetic wave, not for light. So for light, basically you need to have very small scale texture on the surface. But for magnetic wave, basically you can have large scale, and then if you can change the topology or you can change the surface texture of the structure, you can change the reflection of the magnetic wave. So I think those two examples are quite relevant to the scale, as you mentioned, around maybe from centimeter to tens of centimeter. It's somehow it's doable, but I didn't try that in reality. Just have some very brief idea. I think maybe Yihui has more concrete answer to this kind of question, basically. Yeah.
Okay. Thanks. So my understanding is that it's possible that to combine these morphing structures with other functional materials or structures, so that could be quite useful while we figure out the morphing principles first. Right?
That's true. That's true. Definitely.
Okay. Yeah. Okay. Thanks.
It might also be important to include the fabrication and what kind of materials and devices that can be compatibly fabricated using the same technique.
Yeah. That's also very important.
Yeah, that's a simple addition.
Yeah, thank you.
Thank you very much, Yifan and Yue. Michael?
Can you hear me? Okay.
Yeah.
Yeah. Thanks for the great talk, Mingchao. I wanted to
Thank
ask
you.
about the hierarchical tessellation stuff.
Yeah.
So I think I might have missed it. So when you decide your local tessellation, how do you then build that into the substrate? Is it 3D printed or?
Yes. So, it's 3D printed, as you see here. Sorry, I can use my laser. So as you see here, actually, we have an algorithm to do the tessellation, and then we place all the particles on a flat surface, and then we use 3D printing to fabricate all those particles.
Okay, so I guess once you've kind of then fabricated it and you create your structure, I guess then the shape is fixed, right, by the
Yes.
tessellation that you choose. So yeah, I was wondering if you thought about whether it's possible to have something that could reconfigure to a different shape and somehow change the tessellation sort of on the fly. I don't know.
Yeah. Thank you very much for this very wonderful question. So indeed, we do consider that before. So I worked this project with Jimmy and Yifan. So during our when we work on this project, so we are considering if we can make a reconfigurable morphing structure. And this maybe it's hard to make multiple shapes, but at least we are considering if we can make our structure can morph to 2 particular shapes. So this is what we are considering. But finally, it turns out that it's quite challenging to. We can design, in principle, we can design that kind of particles, but it's challenge to challenges is in both the fabrication and also the actuation. So fabricate those for those kind of, for example, you want to make one shape to morph to 2 targets. So you need to have some local geometric texture of the particle. So the fabrication is quite challenging. This is one point. Another thing is that you need to have very precise the actuation to trigger those 2 different morphing states. I can only answer that in principle it's doable, but in reality it's challenging. We are still trying to work on that, but it's not an easy job.
Sure. Okay. Thank you.
Yeah,
Thank you
Michael,
very much.
it's an excellent question. Actually, at one time we were thinking about, just a simple mechanism, just like a pen or pencil. You click it, it goes to one state. Click it again, it goes to another state. So we tried, but not so easy.
Yeah, that's true.
Snap fit mechanism. Awesome.
Yeah.
I can see it's challenging.
I guess the question is, did you think about making the edges kind of buckled beams or something that could be in?
Yeah, we do think about that. So again, it's coming to the challenge of fabrication. So it's a good way to try, but we tried that in our mind. We didn't try that in the lab. So.
Yeah, we were actually at one time considering if the contacting surface or surfaces are not exactly flat but curved.
Yeah.
So you have the possibility of moving back and forth.
Yeah.
But complicated.
Okay, thank you.
Okay, thank you.
Thanks very much, Michael and Jimmy as well. Teng?
Thank you, Dominic. Thank you, Mingchao, for the excellent talk. I have 2 released questions, all about the multi-stable, bistable. You show very interesting example using the bistable design for the robot. And so as you show many examples, the bistable, multi-stable, they are slender structures. So all the energy basically is kind of a bending energy. And so it's true it have snap through, but also like the force generated maybe not very large if you compare to the tensing compression. So basically it's kind of you need to balance this maybe the actuation speed and also the contact force. So can you comment on that? What's the limitation of the using the bistable for the robot?
Yeah, okay, thank you very much. It's also a very excellent question. So maybe Dominic can comment after my answer. My simple thought about this is that indeed, so we are using our beam to store the energy. So it's hard to store too much energy. So basically, this kind of mechanism is more useful for small scale. So here we design this kind of insect scale. Is if you look at the picture here, is around the full robot is around 2 centimeters. So it's quite small, and the weight is also quite light. So if you want to scale up to, for example, meter scale, I don't think this is a good way. The first challenge is that it's not easy to bend a large beam. You need to input quite a lot of energy. It's not an easy way to do that, and so it's indeed. I think basically, I think it's this kind of mechanism is more reasonable for small scale. This is first point, and the second point is that you're asking compared to stretching and compression. Maybe maybe the bending is not a good way for large scale structure. Is that right?
Yeah, that's so I don't know. So I agree with you that for the I think you have to say the body length, but if you go to scale up, it's very hard to go to the 1 meter scale. You can jump 10,
that's true. That's
10 meters. Yeah, so I'm not very sure because as you mentioned, anyway, you need to input the energy. If you're large, you need to input larger energy. So yeah, I think you answered my question very well. And so maybe just a follow-up comments that whether you list a lot of biological example, whether we can find some kind of creature, either plants or animals, they are large and they can also jump very high. Maybe we can find other inspiration from nature, not from insect, but from other animal for the scale up, right?
Indeed, it's a very good comment. I think always trying to find the inspiration from nature to give us some impression how to create a more efficient device. As you see here, for this kind of snapping mechanism only happens in small scale insect, not in large scale animals or something. So I'm not 100% sure, but I think for large scale animals, for example, for human, we always use the squat jump. Maybe there are some similar mechanism for large scale animals, but all those things are not efficient as the click beetle. So I don't have too much a more relevant example so far. If I do get some example, definitely I will share it with you.
Yeah, I have another question also related to the multi-stable or bistable for your meta ribbon. You showed this very nice energy landscape, and I think it's very good that you have two variable, or maybe you find the two important variable to calculate the deformation. And can you comment on for the general structure, multi-stable, bistable? How can you get this nice diagram? They may have multiple variable control configuration, not only 2 or 1.
Yeah, I think it's also very important and excellent question. So here, as you mentioned, we are lucky that here, since we introduced the in-plane kinks and out-plane creases, so we have 2 angles. The phi and psi correspond to the in-plane and out-plane angles. So they are already there. It's clear. So, and also we are clear to understand what's the physical meaning. But for for some of the more complex structures, it's not easy, to be honest. It's not easy to find over what's a K parameter to describe the energy landscape. So the only suggestion I would like, it's not suggestion, only initial thought I think is trying to even for most of the complex structure, you can try to simplify it into a very simple system. For example, our robot, we simplify it as a mass spring system. Even this mass spring system is not fully reproduce the physical features of the real robot, but we can more easy to get more physical insight from this simplified system. I think this is one potential way to try for simplify the complex system.
Thank you, Mingchao.
Thank you.
Sorry, I will go to another question in just a second, but I was sort of, while we've got that diagram, I was wondering, is there I guess this energy landscape has come from Wei Cheng's numerics.
Simulation.
Right?
Yeah, that's
so is there a kind of reduced model that you can get a sort of similar energy landscape, kind of tell you what the kind of important ingredients are to give you this transition between snap through?
Yeah, to be honest, we haven't done that. So okay, go back to Tan's question. I think what we have done a recent work with Dominic and the group from UIUC. We have done a recent work about the dynamic snap through of biostable beam. So for the beam, we have again we have a simplified mass spring system to describe the basic physics of the system, so we can more easily to understand the physics of the system. But to Dominic's question here, so for this ribbon system, we don't have that kind of reduced model at the moment. So I think we can try to think about that in the future. Thank you very much.
I want to add a little bit more. I think, sorry, Dominic. I think your results already show the mass spring model can be quite accurate, because most of the slender structure, beam, ribbon, they are geometry nonlinear deformation. If you capture the bending, and then your model is good. So I think, yeah, you maybe make it more rigorous to say the mass spring is not a simple model, it's the right model you want to use. I'm also using the mass spring model, right? It's not a simplified case, because so your structure is just a bending twist dominant.
Yes, that's true. That's true.
Thanks. Yeah. So again, I was thinking about the sort of minimal number of ingredients. I know it's not easy to have just masses and springs, but sort of a small number of masses and springs. Anyway, Zheng, sorry, do you want to ask your question?
Thank you, Dominic. Thank you, Mingchao, for this wonderful talk. So I have two questions. The first one is about your work on the dehydration process of the long leaf. So you studied the dehydration process of that long leaf by both experiments and the simulations. And in the experiment, I think you cut off the two narrow ends of the leaf, and the width of the remaining part of the leaf is almost uniform. Then I can imagine you can model the dehydration process as a plane strain problem, I guess. But if you don't cut off the two ends, then the width of the leaf along its longitudinal direction is not uniform anymore. And it means the edge of the leaf has a curvature. My question is, will that curvature affect the folding process, not the folding, the dehydration induced folding process of the leaf?
Okay, so also another excellent but challenging question. So indeed, we didn't do any quantitative measurements about that particular case, but we do observe some, as you see here, observe some this kind of the full range of the leaf will fold, but quantitatively, I believe there will be some effect since the boundary due to the boundary constraint on the folding process. But how does the effect can be quantified? I have no answer so far. But instead of those kind of effect on the folding process, one thing I would highlight here is that, as you say, if you keep the full piece of leaf, you will see the deformation is somehow not as uniform as a cut piece. So this is because they have the constraint, the geometric constraint from the boundary. This is also quite very interesting to how to, as you see here, we only explore the folding behavior is the most simplest part, but how to combine the boundary constraint to form more complex geometry is also a challenging problem.
Okay, thank you. So my second question is about the I think another work about the hierarchical tessellation method.
Yeah.
So basically use the hierarchical tessellation method to design 3D surfaces with almost arbitrary geometries. So
yeah,
I can imagine that people can do this kind of design by trial and error method. But
that's true.
It will be very time consuming. So my question is how to efficiently design a target 3D geometry efficiently. Yeah.
So actually here we do have the algorithm. It's a numeric code which can tell you when you input a target geometry, the code will automatically give you what the cut pattern should be. Yeah.
Okay, I see. Another very quick question. So here you show that you can design 3D shapes either which is axisymmetric or non-axisymmetric. So for this, I think the result on the first row is about the axisymmetric geometry. So for this geometry, I can imagine that. So after the morphing, so those tiles can fit each other very well. So with almost no gaps between those neighboring tiles. But for this non-axisymmetric one, so did you observe any gaps between the tiles, especially I think near the that bulging region?
Yeah. So actually, it's a very good question. It's indeed so. Even for the axisymmetric structure, so in the real experience, so it's not easy to get a perfect match between the neighboring edges. So you're right that for those kind of non-axisymmetric structure, the gaps it's more significant. Especially for actually it's not only about the axisymmetry, it's more about the how complex the curvature is. So more complex the curvature distribution is, you will more easy to get the gap. So it's also related to how to control the actuation. So if you can now we are using the way to insert a tendon to trigger the deformation. So this is basically is controlled by our hand. It's not so apparent. So if you can have a more controllable way to do the actuation, you may be able to minimize the gap. But in the real experience, it's not easy to get rid of all the gaps.
Okay, thank you, Mingchao.
Yeah, thank you.
Thanks very much. KG?
Yeah, this is KG. Thanks, Mingchao, for a very nice talk. And I'm going to ask some kind of high-level question because I don't particularly work on this field, so I question might be naive. So the first thing I kept thinking is that I'm always intrigued by how many fascinating structures can be achieved using mechanics principles, right? As you introduced, using string mismatch, hierarchical structure design, elastic instability, and others, those mechanics principles. So as someone not working in this field or someone generally interested in this field, for instance, if I want to achieve a structure, I would like to look up either a website or some toolbox that how to achieve that kind of structure. So my question is now, if let's say we use the same mechanics principle, can we have kind of library or like encyclopedia that what kind of structure can be really achieved by our mechanics principle? Is there such a database, or is this such a worth effort to make such a library?
Okay, yes, thank you very much. This is not a naive question, it's a very high-level question, actually. To be honest, to my knowledge, I don't think there is this kind of library or database available. When we are writing this review paper, I do talk about this kind of idea with these two first author of this review papers. We are thinking maybe we can make, or it's not a very comprehensive database, but at least we can have more comprehensive rather than here. This is not a long review paper, it's a short review paper. So we only summarize 5 different types of mechanism, also based on mechanics. It's there as Yihui or some other one mentions that you can also include some smart materials or different types of actuation, something. So we are thinking that maybe we can make a small database or a small table to summarize all those information, both mechanics or the other function materials together, to tell you how to make the choice if you want to make particular type of morphing structure. But your question is much more high level because you are also wondering which type of method can give you different target structures or target shapes. So is there any direct guide to show the link between the method and the target? So I think this is something I even haven't think about that before, and I don't think there is a database available. To say if this is worth, definitely I think it worth to have this kind of database. If that database is available, it's much more useful because you don't need to think about you don't need to do the trial and error to test your design. You can at least get the first step impression from those database to make the relevant method to create your target structure, I think. Yeah, I'm not sure if I answer your question properly, but this is what I can thought, yeah, at the moment.
Can I add to that comment? I like Mingchao's answer, but maybe let me turn the question back to you, Ke Jie. Can you catalog all different shapes of flowers? Can you?
I really don't. I really don't know.
Different shapes of plants, for example, right? When you ask plant biologists, most of them would say, "Oh, these shapes, the phenotypes they call them, are determined by DNA." But the question is, do mechanics principles also play a role in forming of these shapes? Maha at Harvard actually started many years ago to do some work on that, and we did. We had a fairly recently, 2022, I believe, a review paper, plant leaf morphogenesis. The first author is also this student, Ke Guo, publishing molecular plants, and also trying to ask these questions. In other words, the question whether mechanics plays a role in forming different shapes. I don't think anybody has done that. You raised a very tough challenge for.
Yeah. Thanks, Jimmy, for the additional comments. It actually brought me 2 additional questions. I'm not taking too much time, so hopefully it's a little bit easier. So that's my personal wish. Like I can think as engineer. Let's say I want to design a structure. I want to achieve certain function, but I don't know how to achieve that. Then I would like to look up something. I would like to look up on the internet and see, oh, this is a structure. Let's say I use ChatGPT, right? This is the structure I like to achieve. Tell me how I can achieve that. I don't know why that, but tell me how I can design my hierarchical structure and then to achieve that. I wish there's such a guidance or a small library, as Mingchao said, that then we can look up something. Anyway, so that's my personal wish, and I really don't want to place any tough challenge to this field. So yeah, back to Jimmy's comments. This actually bring up my 2 another questions. One is I think I made a hypothesis when I asked the question. I thought the mechanics principle has been well studied in this field, as is just like Mingchao showed this very nice slides. a few different mechanisms. So I think it's maybe is there still further development on about the mechanics principle, like the previous question, for instance, we consider this geometric ratio, then is the plate or the beam? So is there still further need of the mechanics principle to get a better understanding in this field? So this is the first question. And the second question is, again, following Jimmy's comments about the how do we correlate the mechanism versus the biological system, right? So we can propose those mechanics principle to achieve this certain structure, but from a biological point of view, how do we really correlate what we are talking about in the mechanics language versus the biological principle? For instance, we're talking about the jumping insects, right? And then we use the mass spring model, and there's a stiffness parameter. Then from a biological point of view, then what does that stiffness really represent in the insect, right? What is that? So how do we make a better connection between the mechanics modeling versus the biological principle? So this is my second question. Hopefully this is a little bit easier to answer, but this is my question. Yeah.
Okay, thank you very much. I can try to answer the first question. I guess Jimmy may have better answer for the second one. So for the first question, or maybe for the first question, maybe Dominic will have a better answer. I will try to answer it first. So as you mentioned, actually those kind of mechanics principle is well studied. It's not some new thing. So what we are doing is just trying to link those things to some particular field. For example, here what we are interested in is about the morphing structure design. So either the stream mismatch or elastic instability are not some new topics. So the challenge is that how to apply those kind of simple mechanism to some particular design tasks. I guess this is some challenge thing. And also about some new things, I think it's hard to say some new knowledge. So we don't. I don't think we need to build some new mechanics knowledge to solve this problem. But a challenge is that how to pick the most relevant mechanism or most relevant method to solve those kind of problems. Especially, I think one thing interesting for the morphing structure by applying mechanics is how to achieve the inverse design. So we have done some work with Dominic, and also Yihui has done very beautiful work about the inverse design by applying mechanics principle. And those things, I think, it's a good example to show how old mechanics can tell us new things in this field. But maybe I'm not sure, Dominic, if you have any comments for this
No, I was
question.
just going to say, I mean, I think somehow there are lots of different strategies, right, for designing particular shapes, and maybe the question that needs a bit of thought is, how do you measure the complexity of a particular solution to get a particular shape? So there's kind of a trade-off between, okay, using the origami you can get within some distance of a particular shape, but using the tessellating blocks you get some other distance. And it's really a question about, well, complexity in lots of different meanings, in lots of different senses, but I guess primarily it's about how easy it is to fabricate, and also how robust it is and reliable to actually make a particular shape. But I think those are good questions, Koji. But yeah, we should think about more in the future.
Yeah.
Thank you.
Regarding your second question, Koji, and actually Dominic was here in Singapore, and we went to the Botanic Garden together, and we were all fascinated by the kind of biological diversity that present. Maybe Dominic, you can make a few comments about biological processes or guiding principles versus mechanics. You want to say a few words?
Say something. I'm not sure I can say anything particularly profound. I mean, I guess one of the things that I'm thinking about, maybe it came across a little bit in Mingchao's talk, was about, a lot of this is done in practice by moving water around, right? So that's something that I think we haven't really thought about so much in as a community. Maybe we've thought a lot about, you know, in soft robotics, moving air around, so dealing with things pneumatically, or as Mingchao showed very nicely with having his wires that are actuated in different ways. But actually, a lot of what's going on in biology that maybe we haven't thought about so much is just moving water, and then the constraint is really not so much about pressure, but it's a constraint about volume, and changing the volume of different elements and letting the pressure be whatever it has to be. So that's maybe the main thing I'm thinking a little bit about in the moment, and maybe others would find that worthwhile to think about as well.
Indeed.
There are some people who've thought about the dynamics of moving water around. So I know Amir Gat and Moran Berkovici in Israel have thought a little bit about things like that as well.
Yeah. So going back to Koji's second question, I think the more challenging part is not just the morphing, but for biological systems, they grow. So they are not stationary. The shape and the tissues themselves will morph, will change volume as they grow. And so when we ask biologists, how do these shapes form? Do they really form by taking the instructions from DNA and building one molecule at a time? The answer is most likely no. What biological systems control is they control the growth rate. They control, for example, the proteins, the hormones that would generate different growth rate. Then it goes back to Mingchao's statement. The basic principles, the differential strain or mismatch strain, or the instability, the snapping behavior, these are all mechanical principles. So by growing with different rate at different locations, you generate residual stress. And that may trigger some of these mechanical morphing behavior. So this is maybe a very simplistic explanation of some of these processes. But indeed, it's a fascinating field. We only touch the very surface of this.
Thank you very much.
Yeah, thanks very much, Jimmy. Wei, do you want to?
Thank you, Mingchao, for the really wonderful talk. I really enjoyed the talk.
Thank you.
I have a question here. Particularly, I have been working with you on the morphing structures. One of the example I'm thinking about is the morphing wing. And particularly, they use the morphing behavior to control the aerodynamics. For that, actually, you wonder, like, you want to hold the morphing at a specific location. So that's actually for particular aerodynamics, they need to be stay there. So I wonder, have you think about any way we can actually design the structure that they can morph to a specific location and stay there without supplying additional energy? So this is more like something like a multi-stable structure. You have multiple stable states where you morph there and don't need to supply actual energy. So that's my question.
Okay, thank you very much. So indeed, we have thought about that before. I do have work with Dominic. We consider as you see here, this structure is inspired by the chocolate mold in the kitchen. So it's a very good demo to show that how can we make a multi-stable morphing structure. As you see here, we have a plate with multiple dimples, and then we push it down. We can control the global shape, and this structure will be stay there. So, but to be honest, this is a very preliminary exploration. So we didn't reach the point to do the inverse design or something more precisely control. Here we just show that we can control the shape and to stay there without input, without the input of energy. So I think I agree with you that the morphing wing is also morphing is a good example to show how does the morphing structure can be applied to, and also a grand challenge for morphing wing is that how to maintain the morphing state for a certain period of time. So I'm not sure if this is some relevant way to reach that point, but I think it worth to explore in the future to integrate this kind of multi-stable units to design the morphing wing, something like that.
Thank you.
Okay, thank you very much.
Sorry, you're thinking really of a morphing, the plane wing that you showed, Mingchao. That's what you mean.
Something like that.
Okay.
Yeah.
See, that's interesting. Okay, thank you. Oh yeah, Jimmy, sorry, you were gonna ask a question as well.
So Mingchao, excellent talk.
Thank you very much.
A couple of maybe not really questions, but let's call them higher level questions. I think two aspects are for biomimetic systems. Two aspects are very important. One is the dynamics aspect of morphing structures. So the question is, where do you see the major opportunities are? What are the major challenges if we want to implement or study more carefully the dynamical system? This is first aspect. This second aspect that we as a community really haven't thought about too much, which is the effect of feedback. So biological systems, when you change something, you not only change the states of that, but also change the pathways through feedback systems. Do you see something that we can do in that area, maybe to contribute to the understanding of biological system better?
Okay, thank you very much for indeed these are two high-level questions. The first one about the dynamic process, I think indeed it's most of the biological system involves the dynamic process, but we didn't take into account for most of the morphing structure design. And I agree with Dominic that maybe, for example, if we consider the fluid flow inside of the structure, or use fluid flow to trigger the morphing, it definitely necessary to consider the for example the flow velocity, how fast you pump the flow. This will affect what type of final configuration you can achieve. But how to consider this kind of dynamic effect, or how to integrate this kind of dynamic effect into the model, to be honest, I think it's quite challenging. So as far as I know, even for simple structure like the beam or ribbon, the dynamic properties, especially involved if it involves the instabilities, it's quite challenging to fully understand what the dynamic instabilities will affect the behavior. So I agree this is a good opportunity to explore, but it's quite challenging, to be honest, especially for theoretical analysis. So another question is that about the feedback control. Indeed, I think it's a very even we don't consider the biological system. Recently, one as far as I know, one hot topic in the software robotics community is to consider the self-sensing and control, which means you can sense your shape and to integrate some feedback control to adjust your current configuration. So this is one challenge thing, and also very important if you really want to make a robot can behave like a real biologic system, like an animal or something. as we know, for any animals or for human being, for ourselves, we definitely have very good feedback control system, so we can make any kind of adjustment for not only about our configuration and also about our action to different tasks. So how to integrate the feedback control into the morphing system is it's an emerging topic in recent, I guess, at least in recent 3 years. I have seen several papers are trying to integrate a lot of sensors and actuators into, or for example, into plates or into a shell structure, and then use those sensors to detect the X-ray interaction and integrate some feedback control system and to change your actuation non-uniformly to adjust the global shell. This is but to be honest, those are very preliminary exploration in this field. There are still a lot of opportunities to explore in the future, I think.
So this is towards the so-called engineered active matter or active system.
Yeah, something like that. Yeah.
Thank you.
Okay, thank you.
Sorry, I was gonna ask about the drying leaf problem as well, whether in terms of trying to think about dynamics, I bet there was a bit of conversation in the chat about that as well. But I was wondering whether there's anything interesting to be done by kind of designing, if we're doing this artificially, should we design more complicated channels for the water to evaporate from, so that it can so we can actually try and control shape dynamically? Or if we know, thinking about 4D printing and so on, you don't just want to control the shape it goes to. Ultimately, you want to control a whole series of shapes that it journeys through. And I don't know whether there's in this sort of picture you've got in the bottom right on this slide, whether there's any sort of way of controlling in a bit more detail how, not just kind of the final state, but also the stages that you go through as you dry.
Okay, so I think it's a very good point that as I have shown some example about the hydrogel morphing. So normally people are considering the swelling process rather than the evaporation induced shrinking process. I think there are some work considering the non-uniform swelling and to induce some complex geometry. But the point you raise up is the way around. So how we can control the operation non-uniformly or dynamically to trigger the different types of morphing structure. To be honest, I didn't see any examples so far, and I think there should be some chance for us. For example, this kind of umbrella structure, we can. Because the water in operation mainly happens in the hydrogel region, so we can control the cross-link degree of those hydrogel. Now we make almost uniform for all the channels. Maybe we can change some of the channels to be more cross-linked, some others more or less cross-linked. So maybe we can control the evaporation rate at different level locally.
Yeah, that's the sort of thing I had in mind, either the evaporation rate or just which bits dry first, and then thinking about trying to do that. Okay, thank you.
Yeah, thank you.
I don't know if there are other questions. It's kind of was very busy earlier on. Thinking a little bit about the stuff you showed with the magnetic cilia as well. I don't know whether again, I don't know how easy it is to use Wei Cheng's numerics to just to kind of explore the design space, but also to get ideas for where might be interesting bits of design space to go.
Okay, so Yeah, so instead of the magnetic stuff, we do have some ongoing work with WeChain to explore the optimized design or inverse design of this kind of jumping robot. So what we can do is trying to, because the numeric simulation based on different discretized different geometry is quite efficient, so we can easily run a lot of simulation for different space of the parameter. So, for example, what we did is in our ongoing work is that we run around 100 of thousands of simulation with different given parameter space, and then we use that data as the training group to train a neural network, and then we can use that neural network to be it's a design tool or inverse design tool to tell you. For example, if you have a jumping robot, if you want to reach some certain location, how can you choose the particular parameters to reach that point? So we almost finished that work and hope we can share that results in the near future.
Okay, that sounds interesting.
Yeah,
you being a bit. I mean, I think another thing that we've thought a little bit about is different substrates, but I wonder if it's possible to kind of tune the shape or whatever of the beam as well in a similar way to try and get different kinds of snap through. And
so now what we are changing is the angle of the at the edge and also the compression, the end shorting.
Okay.
Yeah.
But it's kind of not anything, so it's kind of a global, you're changing kind of global measures rather than
that's true. Yeah, that's true.
Okay. That's interesting. So it's kind of quite, sorry, without, I know you're doing a lot of simulations there, but in some ways that's quite a small design space, really.
That's true. That's true. So it's for any given robot structure, you can only turn the angle and the end shorting in your not too large parameter space. But what we have done is that we figure out those kind of accessible parameter space, and then we run simulation in this space, and then tell you how to make the choice of those parameters for to reach some certain location.
Okay, thank you. That's interesting. Okay,
I was
don't know
just
if
going to say,
sorry.
do you not also have the compression rate of the spring?
The release rate
as well.
Yeah.
That's like a dynamic.
It's not so clear.
So the rate at which the top spring compresses as well, right? Is that something you can play with as well, or?
Maybe, but we haven't tried that. So what we have done, I guess we don't consider how fast you compress a beam. This is yeah, I don't have a clear view what will happen if you compress it slowly or you compress it faster. So maybe you can trigger different types of different. I'm not sure. Maybe you can trigger either snap or either the asymmetric or the symmetric snaps or something.
Yeah. So I mean, that would be... Go on,
I was just going to say, I thought that isn't that what causes you got the symmetric and the asymmetric snap throughs? Is it not caused by the different compression rate, or is that?
Yeah, you're right. So there's
something
some
else.
work that published last week that showed that when you release, it's actually releasing rather than compressing. You release the ends to let the snap through happen, and if you go very fast, it's symmetric, and if you go very slowly, then it's asymmetric. And I guess that sort of has, well, maybe it's a bit binary for what Mingchao wants, because Mingchao will probably presumably say that, oh, just jumping, if you want to just jump vertically, then you just want to stay as symmetrically as possible.
Yeah, maybe it's sorry.
No, I was going to say that I sort of think that having kind of different beam shapes or something so that you control how the snap through happens and when when energy is released might be interesting, just to actually try and get something a little bit more subtle where.
To jump in, another way to think about optimizing could be, there's some energy that's being lost as the beam is beginning that snap through process and changing shape, but not contacting the ground. And so are there elements you can add to the beam so that you're kind of all of that elastic energy as it's maybe going through those mode shapes is pressing against something and generating a reaction force and then enabling you to convert that elastic energy into kinetic energy. And so maybe it's about optimizing for where are you losing energy in the system structurally as a way to better convert that to, kinetic energy.
Yeah, that's a really good point. And it's kind of what I was sort of, aiming at a little bit, in that when we did the kind of the spring model with it, I think Mingchao kind of showed the restriction height, so that how much of the arch is kind of sticking out the bottom, this HR here.
Yeah,
that's sort of exactly what Doug's saying, that actually what we found is that you're kind of better off touching you want to kind of touch the floor as soon as possible, so that you then kind of unload while in contact. Whereas if you kind of snap and are going very, very fast, then you kind of hit the floor, you lose all your kinetic energy and make a big noise, but you don't actually get any jump out of it. So I was kind of wondering if you can kind of distribute mass or distribute bending energy along the beam in such a way that you kind of actually release that bending energy rather than wasting it in hitting. Sorry, Doug's going to do a demo now. I don't know.
I was just going to say it's the same as
EML
taking a
first.
popper and having it jump off of a table or having it jump off of your finger, and it'll go significantly higher if it's sitting on the top of your finger.
Yeah, and I think that's absolutely right. It's kind of this. I think. Well, I don't know. We've talked about that before, Doug. I don't know whether anyone's sort of quantified it, but with the restriction height, it's kind of exactly that effect that you're.
That's true. Yeah.
But I guess playing with so Doug's finger is great, but if you're making a robot, generally a robot wants to jump off something flat, so you don't really get to choose the geometry of your substrate. So you should choose the geometry of your
robot
snapping, of your robot and the bit that's actually snapping, so that you get as much energy as possible. I think that's interesting and a really good idea. Great. I don't know if there are more questions, or we might be reaching the point where come to an end of the webinar now. Mingchao, I think you can tell by the level of interest and questions that we've generated and the long queue we had at various points.
Yes, thank you all very much.
You really engaged everyone with some really nice, a combination of some mechanics and some nice applications, some really beautiful experiments, lots of nice simulations and movies. So thank you very much for a really inspiring webinar with lots to think about, lots to talk about in the session after your talk, and I think also maybe some conversations to carry on in the future as well. So thank you very much, Mingchao, and thank you everyone for coming. It's been a really good conversation, and I think there'll be lots more coming out of this in the future. So thank you very much, everyone.
Thank you all for coming.
Thank you.
Bye.
Thank you.
Bye.
Bye-bye.
Thank you.
Thank you.
Thank you.
Okay. No, I thought John would have something to say, but that's okay.
Oh, sorry.
Okay, sorry. So maybe I can say something about our next webinar before we really wrap up Mingchao's webinar. So our next webinar will most likely be in September. So we're still negotiating with our next speaker about the exact date. So because we all know that the July and August will be full of international conferences and international travels, so we don't want to stretch our people too thin. So yeah, I think September will be so it'll be good for our next webinar. So please stay tuned. And
all EML webinars are archived, so you can go back and watch them again on YouTube anytime you want.
Yeah. Okay. So
All
maybe
right. Thank you very much.
have a good night and have a good day.
Okay. Thank you all.
Yeah, thank you
Thank
very
you.
much, especially
Bye.
those staying up very late. Bye.
Thank you.
See you.
See you.